Hello, today we will be solving this problem called the Josephus problem 2. It is similar to the previous problem. The only difference here is that the jump is not by 1, but rather by some arbitrary value k. So let's read the statement again. Consider a game where there are n children, numbered 1, 2 to n, in a circle. During the game, repeatedly k children are skipped and one child is removed from the circle. In which order will the children be removed? The only input line has two integers n and k. N is as large as 2 times 10 to the 5th and k can be as large as 8 billion. So we can see here that k may be larger than n, and several rounds around the circle may be required to remove one child. Like in this example here, we would go ahead and check out this example. So in this first example, there are 7 children, 1, 2, 3, 4, 5, 6, and 7. Okay, and we said we're gonna start from 1 and we're gonna skip 2 children, so we're gonna skip this one and remove 3. So 3 is removed. Then we're gonna skip 4 and 5 and remove 6. So 6 is removed. Then we're gonna skip 7 and 1 and remove 2. So 2 is removed. Then we're gonna skip 4 and 5 and remove 7. So 7. Then we're gonna skip 1 and 4 and remove 5. Okay. Then we're gonna skip 1 and 4 and remove 1. And finally we will remove 4. So is that the answer? Yes, 3627,514. 3627,514. So as you can see here, let's do one other example first, like with the same values but with a different k. So here, if k is 8, then we're gonna start from here and we're gonna skip 1, 2, 3, 4, 5, 6, 7, 8 and remove 2. So we're gonna remove 2. Then we're gonna start from 3 and count 1, 2, 3, 4, 5, 6, 7, 8 and remove 4 and so on. So this is just to point out that k can be larger than the size of our array. And now, instead of writing our the IDs of the children in a circle, let's go ahead and write them in a straight, like in array fashion. So we have 1, 2, 3, 4, 5, 6, and 7. In this first example, k is equal to 2, and the starting position, the start, is equal to 0. So, and we said that the first element we removed was 3. So what is the position of this 3? It is precisely 0 plus 2. Okay, so in order to know what position to remove, we just take our starting position, add k to it, and see what that gives us. So 0 plus 2, this gives us 2. So that's why we removed the value at the second position, and that was 3. Okay, and now if we remove 3, the array becomes something like this. It becomes 1, 2, 4, 5, 6, and 7. K is still the same value too, and our starting position now is this 4. But since we removed this 3, 4 got the value of the last removal. So the last removal was at 2. So the last removal was at 2. So when we removed that 3, 4 got the value of the last removal. So the start just got the value of the last removal, which is 2. So we are at this position now, and the value we're gonna remove next is just gonna be, the next value of remove is just gonna be start plus k, which is 4. And this makes sense. That's why we're gonna, so this is 0, 1, 2, 3, 4. That's why we removed 6 next. Okay, and now as we said, the array will become something like this. And start again will be at position 4, because 7 took the place of 6. And the next removal this time will be 4 plus 2, which is 6. But as you can see, our array is not does not contain 6 elements. It only contains 5 elements. That's why we have to take this value modulo the size over our array, which is 5 in this case, and this would give us 1, which means that we have to remove this 2 because it is at position 1, and that's precisely what we did there. And our start will be again 1, and the array becomes 1, 4, 5, 7, and we'll do the same thing again. 1 plus k is 3, and 3 mod 4 is still 3. That's why we will remove the value at position 3, which is 7. That's why we removed 7 here, and the start again will become 3, because but it will become 3 as we did here, because we removed this value. But notice here the size of our array is 3 as well, so we need to take this modulo 3, which will give us 0, which means that our starting value now is 1. So what we notice here is that calculating the starting value and the position to remove has to always be taken modulo the size of the array. And we proceed again, so we're gonna start from 0, and the value to remove would be just 0 plus 2 modulo 3, which is fine because 2 modulo 3 is just 2, so we're gonna remove 5. That's what we did there. And then we're gonna, so the next value of start would be 2, but our array is of size 2, so we gotta take it modulo 2, so that would give us 0. So the next value of start would be 0, and our array only has 2 elements left, which are 1 and 4. And then so the value to remove would be 0 plus 2, which is 2, mod 2, which is the size of the array, which would give us 0. That's why we removed 1 here. And finally, the next value, so start will just get 0 mod 1, which is 0, and our array only has 1 value, which is 4. Then we'll just remove this. So this is pretty much it, but there is an issue here. So basically we can calculate the value to remove pretty efficiently in O of 1, so we know what value to remove. But what we can't do efficiently is this process of removing a value and generating a new array. In order to do this, each time we generate a new array that is 1 element less than the previous array. So we're gonna start with an array of size n, then we're gonna generate an array of size n minus 1, and we'll keep going this way until we reach 1. So at the end we will have gone through n times n plus 1 over 2 elements, which is the same as n square elements. So our total complexity would be n square, which is too much. So we gotta ask ourselves now of any data structure that would allow us to perform the following operations. So we need to remove elements, insert elements. So till here it's fine. We could just use a set and it would allow us to do both operations. But as you saw, at each um, step, we were asking ourselves what element is present at this and at such a position. So what this means, we need a data structure that has these functionalities of a set, but also that has functionalities similar to arrays. So we need to know like a value at x position, for example, or like what is the kth smallest value, and these two are like equivalent, and we need to perform this operation fast as well, so at most log n time in complexity. And there exists a data structure that would allow us to do all of this, but it is not a standard, it is not a data structure that belongs to the standard library. So this data structure does not belong to the standard library of C++, but can be obtained using the GNU compiler. So if we see here, these are called policy-based data structures, and we can use them using the GNU compiler, and there are many of them, but the one we are interested in today is the ordered set. So ordered sets are part of the GNU C++ policy-based data structures, and these data structures allows us to do the following. So ordered sets are data structures that keeps the unique, so the elements have to be unique, and we don't have an issue with that in our case because, as we saw, the ID of the children are unique. So it keeps the unique elements in sorted order, and it performs all the operations as performed by the set data structure. So that would allow us to do the insert and the erase in log n, and performs two additional operations also in log n complexity, which are the order of the key, which tells us, so this is pretty much the same as looking the position k in an array. It tells you the number of items strictly less than k. No, so this is the opposite. This is what I meant. This is this operation find by order k. It gives you the kth element in a set, counting from 0, so it's 0 based. So this is pretty much the same as looking the position k of an array. And in order to use this data structure, we would do the following. So we will have to perform a few includes. So we would include this associative container and this tree policy, and we will have to use this namespace. It's the GNU policy-based data structure. And finally, this is how we declare our ordered set. For those of you who don't know, this template here is just so we could use any type here. So we could just, for example, if we wanted to use an ordered set of ints, instead of this we just put int here and int here. So this first element is the type of elements that we're gonna store in our ordered set. This second element is null type because we want a set and not a map. We would fill this if we wanted a map, and this would be the second element of our map. Then this is our comparator, This means that the elements will be sorted from smallest to largest with respect to this type. If we wanted the opposite, we would use greater. And this is the data structure, or actually the tree that we're gonna use. So here we use the red black trees, and these would allow us to perform the operations we mentioned. And this is the method to use to update the tree after each modification. And finally, these are the methods we described. So for example, if we had our ordered set and inserted 1, 2, and 7, and we said and called our set st, and we said st find by order 2, this would return iterator, let's call it t. And if we printed the value stored by t, so if we dereference t, it would give us 7, because if this were an array, the element at position 2 would be 7. And this order of a key, so if we said st dot order of key of 7, this would give us 2, because the element at 7 is at position 2, or rather there are 2 elements strictly less than 7. And remember, all these elements are unique. So back to our problem. In order to solve our problem, we will just do precisely that. We will insert all elements, like this would be our set, and let's solve the case for 7 2 again. We will insert all elements in the set, and we said there is a start position and a remove position. At the beginning, this is 0, and this would be 0 plus 2, which is 2. So we would look for the element at the second position, which would be 3. So we would print it and remove it. Then again, this value becomes the starting position, because we're gonna start from 4, and the position of 4 in this set now is 2. Then we're gonna add 2 to it, so this becomes 4. Now we look for the elements at position 4, and that would be 0 1 2 3 4, so that's 6. So that's 6, and then remove 6, and we keep on going as we described above. The only difference here is that using this data structure would allow us to solve the problem in O of n log n instead of O of n squared that we described above. So this is it. Let's go ahead and check out the code. So this is the code. As we said, we're gonna include that policy-based data structure, associative container, and tree policy. Then we're gonna declare our namespaces, which are std, the standard one, then the GNU policy-based data structure namespace. And here we're gonna declare our ordered set as a template, instead of declaring ordered set of int and having to change it for each type we want. Then we will go ahead and declare our 2 variables, and n and k, read them, declare an ordered set of ints, because all elements will be only as large as 2 times 10 to the 5th. We'll call our set children, and we will insert into it all elements from 1 to n. Then we said we're gonna initialize our start position with 0, and we will go inside this loop as long as the size of our set is greater than 0. So our start position, as we said, in order to keep our start position and position to remove within bounds, we'll always modulo them by the size of the array. So we're gonna modulo the start position by the size of the array, and the position to remove would be just the start position plus k, and we're gonna modulo that by the size of the array. Then in the next iteration, our starting position will just be the position we just removed. That's why we perform this assignment. And here we're gonna use this method we described, which is find by order, and we're gonna give it the position to remove, and then it's gonna return iterator to that position. And first we're gonna print the value at that position by dereferencing that iterator, and finally we're just gonna erase that iterator, and that's pretty much it. So let's go ahead and submit. So that worked. I will put the links I showed in this video as well as other links in the description box, and I invite you to delve deeper into these data structures. Thank you for watching. See you in the next video. Bye bye.